So, for the median then, so all these medians that go to these midpoints meet at, what's this point in the center again?
Centroid.
That's the centroid. Now the special thing about the centroid is that the distance from the vertex to that centroid is 2/3 the length of the median. So this part is 2/3, this part is 1/3. On this median, now the thing is, it's from the vertex to the centroid is the 2/3 part. So the longer part is 2/3, the shorter part is 1/3. Okay? And it's always 2/3, 1/3. And that ratio, so the ratio of parts is 2 to 1. This one is 2 pieces of this length, and this one is 1 piece, so it's 2 to 1. And there you go. Unexpected. It's pretty crazy. And so then, of course, you have to get out the example problems, and we have to play around with it.
Yeah.
Because of course we do. And a mistake a lot of you guys made on the homework is that when I gave you information, you didn't mark everything you could in the triangle right away. And then later when you tried to figure stuff out, you didn't know what to do because you hadn't already marked it at the beginning. So from the beginning, let's take all our information. I have a triangle. I should have made this triangle much bigger. I had all this space. Should have been bigger. And oh look, I have its medians. Where do medians go from? Vertex to the midpoint. So that means this side and this side are congruent. And this median will go to this midpoint, so this side and this side are congruent. And G to X is a median, which means XF is congruent to XH. Shockingly enough, look, XH is 12. So automatically, what do you know? XF has to be 12 because they're congruent. And so then when it comes over here and asks for FH, which is the whole thing, I know the whole thing is 24. And so then you're going to go to and PF, puff. Let's see, that's from this, oh, what's the point in the middle called? The centroid. It wants to know the distance from the centroid to F. It doesn't tell me how long that is. What do I know? I know that this one down here is 4.
That's 1/3 of it.
And that's 1/3 of it. And the ratio is going to be 2 to 1, right?
Yep.
So if this is 1 4, this piece better be 2 4s, which is how big? 8. And so I know poof is going to be 8. Is 4 1/3 of 12 the whole length? Is this 4 1/3 of the whole thing?
Of course, sure.
Yeah.
And is 8 2/3 of the whole thing?
Yeah.
Yeah.
Okay, so we did it right.
Let's go.
And then it asks for GX. Oh, GX is this whole purple median. Now look at the picture. What could be useful?
The 9.
The 9 would be useful. Now, is that the longer piece or the shorter piece? The longer piece of the median. So it will be 2 of the shorter piece. So how big is this shorter piece going to be? If this one was 9, it'll be 4.5. But is that what it asked for?
No.
No. It wanted the whole distance from G to X. So I'm going to have to take that 9 and the 4.5 to get 13.5.
I had a question.
I have an answer.
May I use the restroom, please?
Since you said please and all.
Thank you, Teach.
I don't think I've ever had a kid actually say that to me.
You're welcome.
It's the first time.
Gotcha. Candy.
That guy's so cool.
Okay? Now there's more examples here. Rather than wasting your time on doing them completely, I'm just going to start them off, and then when it gets to use algebra, we'll stop, because you know how to do algebra. So on this guy, it says point G is the centroid. Well, what does that make these special segments have to be then, if they all meet at the centroid?
Yes.
What things meet at the centroid? Medians. So this is a median, which means it bisects that side. And this is a median, which means it bisects this side. And BD is a median, which bisects that side. And then all the 2/3 crap and ratios and stuff is going to happen too. Now it says FG equals x plus 8. So FG is this little piece of the median. And it says that GA is 6x minus 4. How can I set this up to find x?
Be like 3x minus 2 equals x plus 8.
Okay, so you either have to know that, remember it's a ratio of 2 to 1, so it takes 2 of the little guys to make 1 of the big guys. So 2 of the x plus 8 equals 6x minus 4. Or you could say half of the 6x minus 4 equals x plus 8. Can you algebra from there? I hope so, and you do stuff and x ends up equaling something. Okay? Over on this problem now, it says CG, that's this guy, is 3y plus 7. And CE, that's the whole thing, is 6y. How am I going to do this one? Well, remember, the distance is 2/3, so this piece is 2/3 of this. The smaller part is 2/3 of the whole thing. Okay? So 3y plus 7 is 2/3 of how much? The 6y, the whole thing. I literally used this and translated it. The distance is 2/3 of the whole length. And so 3y plus 7 would equal 2/3 of 6 is how much?
That's like
4.
That's like really big.
And so 7 equals y. It's like crazy.
7.
Okay? And that's the kind of thing you're going to be setting up sometimes in your homework. Some things are not going to be this complicated, but you have to understand how all these ratios and fractions work in order to set up the algebra, which is going to be a really good time. Fun will be had. And suffering will occur. But wait! There's one more.
Yes.
Yes!
Let's go.
All right.
Sorry, I got too excited. Been waiting for this one.
Our last special segment that you can draw in a triangle is called an altitude. Now wait a minute, that sounds like a geography word.
Yeah.
Those of y'all who are in geography, what's altitude?
The height.
It's like elevation. It's like the height. Okay, so I need a victim, a volunteer.
I got it.
Oh, I've got quite a few people. Oh, okay, Elliot, you're being nice and quiet and polite. Don't stand up front.
He doesn't have a do-rag though.
We're going to see what his altitude is.
4'3".
He's taller than me. So hold this to the top of your head. The top of your head. Okay, so define his altitude.
You can't do it.
I'm going to come way over here.
Dang.
He is 12 feet tall.
What? That's crazy. Holy crap, no he's not.
Oh, well, why not? Oh, you have to measure.
There's only 9 feet.
You have to measure altitude perpendicular.
Yeah.
Okay.
What?
So if I hold it up perpendicular,
Twist up.
and he's 5'7"-ish. Okay.
I'm 6 foot.
So the main thing is that altitude has to be measured perpendicular. You don't figure out something's height by going slantwise. So if I want to know the altitude of this vertex, I have to measure it perpendicular from the opposite side. And so that's literally the definition of an altitude. It's a segment from the vertex perpendicular to the opposite side.
Segment. Or is that a D?
Segment from vertex perpendicular to opposite side. Yee! But wait, you say, how many vertices are in a triangle?
3.
3.
Tree.
And so I have to go to this one now, and I can draw another altitude from it. Now, remind me, what makes an altitude an altitude? The 90-degree angle. So when I draw it, is this going to make a 90-degree angle over here?
No.
No. I need it to be a 90-degree angle. So I decide, oh, but this, what's wrong with using the 90-degree angle here?
The thing not there.
It doesn't go through the vertex. So I have to scoot it until I have both a 90-degree angle and going through that vertex.
Are you serious right now?
And then how do I make sure it's perpendicular?
Who's
Put the little box there, and then you know it's a right angle regardless of how bad you drew it.
Let's go.
And so then for this third vertex, I have to come over here and go, okay, I need to be perpendicular. Now look, this perpendicular goes through the midpoint. This is where my perpendicular bisector would be. Is it where the altitude is though? Shh! This is perpendicular through the midpoint. Is it going to be my altitude?
No.
No, because it doesn't go through my vertex. Altitude has to be perpendicular and go through the vertex. The only time the perpendicular bisector and the altitude are one and the same is in an isosceles triangle or an equilateral triangle. But this one, since it's not isosceles or equilateral, the altitude is pushed off to the side a little.
They're not isosceles.
And you have to push all the way over to here to get that nice perpendicular going through the vertex thing going on.
What?
So now I have 3 altitudes.
Implied statement.
And what do you notice about them? They all intersect at a point of concurrency.
Yeah.
Who would have guessed?
Not me.
And that point of concurrency for the altitudes has a name. What is it?
Orthocenter.
Orthocenter. Sadly, the orthocenter is not the center of a circle.
Are you serious?
You know why? Because ortho does not mean circle. No, that's what dent or dont means. Ortho means straight. That's why an orthodontist straightens your teeth.
What about
And an orthopedic surgeon straightens out your bones when they're broken. I never thought about that. And so the orthocenter is just the center of where all these straight lines cross.
Okay.
And guess what? It doesn't do anything special.
Nothing.
Are you serious?
That's a low.
Nothing.
That's
It's not a center of gravity. What? It's not the center of a circle. It doesn't do anything cool with the ratios.
All the lines.
It's not equidistant to anything. It just is.
I think it is very special the way it is.
Now, this does do something interesting. And so for this, turn the page over.
Oh, there's a back.
Ooh, there's a ball. Shh. Now, I think last class, did we talk about where the in-center was always going to be?
No.
Okay, guess what? The in-center is the center of the inside circle, right?
Oh, yeah, we did.
So the in-center is always inside the triangle.
Yeah.
And that centroid that we came up with, what segments met to make the centroid? The medians.
Median.
This centroid is also always inside the triangle. But if you recall, when we did the circumcenter, what makes the circumcenter up? What things meet at the circumcenter?
Angle bar.
The perpendicular bisectors met at the circumcenter, and it moved. Sometimes in the acute triangle, the circumcenter was inside. And you had something like that. But for a right triangle, the circumcenter for a right triangle was on the hypotenuse. And this is the center of a circle, so it's at the midpoint here. It's at that midpoint, and it's the center of that circle.
What does that say right?
On hypotenuse?
On?
On the hypotenuse. It's actually, and that hypotenuse is the diameter of that circle. You don't have to remember that, you just, it's on the hypotenuse. When it's a right triangle, it's on the hypotenuse. And if it was an obtuse triangle, these perpendicular bisectors meet outside the triangle.
Oh, that's actually cool.
And that circle, the bigger the angle gets, the bigger the circle gets. This circle is going something like this.
Blue?
That's pretty crazy.
Crazy, isn't it? This is perpendicular to this side and it bisects it, doesn't it? And this is perpendicular to this side and it bisected it. And I'm perpendicular to this side and I'm bisecting it. And if I take all three of those to meet, they meet outside the triangle.
Can we measure the outside triangle?
And this is still, though, the center of the circumcircle, that outer circle, even though it's outside the triangle.
No matter what, it's going to be the center.
Uh-huh.
Okay.
It's just the center of the circle, but it's outside the triangle. Because the triangle has stretched out so much that it's gotten all pulled over to one side of the circle there. Okay? Now, this orthocenter didn't do anything special, but it's like the circumcenter. When you have an acute triangle, guess where the orthocenter is?
Middle.
It's inside the triangle. It's just boring. But if you have a right triangle, let's look at that. I want to make the altitude to this bottom side. So it's got to go from this vertex and be perpendicular. Isn't that just going to go right down the edge of the triangle? If it's a right triangle? And so the orthocenter in a right triangle is on the right angle. This is the orthocenter. It's directly on the angle. So it's moved from the inside, now it's at the corner. Instead of being on the hypotenuse, it's on the corner of the right angle. And as I stretch this out bigger, the orthocenter of an obtuse triangle is outside the triangle.
Yes.
Crazy, right? And I've got a neat illustration to show you that, but first I want to go through and remind ourselves, how are you going to remember what thing goes with what? Which segment goes with which center? And it's an odd peanut butter cup may contain apple butter instead. And it always goes in pairs. So y'all told me last time that peanut butter made you think of perpendicular bisector. And so the cup, the C from the cup, told you to go with the circumcenter. And that apple butter went really nicely with angle bisector, and so the instead told you to do in-center. So what do you think this A in and stands for?
Like altitude.
That's going to be altitude. And what's its special point of concurrency? The O for orthocenter. And the M for may contain, what do you think that M is? That's median. That reminds you to think of median. We'll go with contain. What's that C going to be? Centroid. Okay. And notice perpendicular bisector is really long, isn't it? So its C word is circumcenter. The median is a short word. So its C word is also short. So circumcenter goes with perpendicular bisector, centroid goes with median. Do you have to use this to remember it all?
Not at all.
No, but we thought we'd give it to you in case you wanted to use it to help yourself remember all the things. Okay? Now,